Hi everyone. Today we're going to work our way through kind of two objectives. The first one is we want to really start laying the groundwork for how we use trig functions, what their use is for us, their benefit at times. Secondly, what we want to do is we want to kind of move towards where we're going to go with graphing trig functions. So today's going to kind of feel like it comes in two parts. A little bit of a first part, which is a consolidation, and then our second part is really an introduction into where we go. So the first thing I'd like you to do, I'd like you to go through and graph each one of those functions for the given domain. So you'll notice on the graph what the scales are. What this would be a review from our last lesson. So if you're able to go through and produce the graph of each one of those functions, sine x and cos x, without looking back at your notes, then this is going to give you a real good gauge that you're where you need to be. So what I'd like you to do is just pause the video right now, and I'd like you to produce the graph for both of those functions. Okay, we're back. So hopefully we can go through and we can use our maximums, our minimums, and our zeros to graph each function. So we know that our sine graph starts at the origin, and we then increase, and we hit our first maximum at 90 degrees. That has a value of 1. We come back and hit our next 0 at 180. We hit our minimum at 270, which has a value of -1, and back to our 0. With those key points, we should then be able to connect that with a smooth curve, knowing that we are curving down the whole time for that portion, and then curving up the whole time for that portion, and we should be able to produce a pretty decent looking graph. Okay, let's move on to cos x. So we know that cos x starts at its maximum, so a value of 1, and then it falls. And so at 90 degrees, we would then hit its 0. At 180, we would hit its minimum. At 270, we would come back to a 0. And at 360, we come back to our max. And so with those key points, we can put on that curvature of curving down. At the 0, we switch to curving up. And then at that 0, we start to curve down again. And we should be able to produce the blue graph for our cos x. So just a little bit of review, and as I said, if you were able to sketch both of those graphs, graph both of those functions, then you've got what you need from the previous day's lesson. So what we want to do now is we'd like to go through and actually change one of the key features of that graph. And so as you've been working your way through our last lesson, we used a scale of 0.2 on our y-axis. We will very rarely use a scale of 0.2, and quite often we're going to end up using a scale of 0.5 on our y-axis, and you'll kind of see a reason for that as you progress and work your way through these functions. So what I'd like you to do now is pause the video and go through and sketch each one of these graphs with the changed scale on our y-axis. So you'll notice that our scale on our y-axis is 0.5. Now I'd like you to produce those graphs. So go ahead and pause the video. Okay, we should be back. And we should be a lot more comfortable in moving through that. So we know that our sine graph starts at 0 and rises. We hit our maximum at 90 degrees. Our 0 at 180. We hit our minimum at 270 and our 0 at 360. We now connect those with that smooth curve, knowing when we're curving up and curving down, and we get a pretty decent graph. Our cos curve, we know, starts at the top at its maximum, and it falls. 0 at 90 degrees, minimum at 180, 0 at 270, maximum at 360. And now we do the same thing, and we know when we curve up and curve down, and there we go. So again, a little bit of review, and that's really going to give you a good idea of whether you have what you need and whether you know what you need about your sine and your cos graphs. So now I want to kind of move on and specifically talk about how we use those trig graphs. And so what I'd like you to do is just take a look at question 3. And you'll notice that question 3, the problems that you're asked to deal with in there are problems that we've dealt with last unit, if you want to think of it that way. We've dealt with rotation angles before. However, these may have been some situations where maybe we struggled a little bit to be able to work our way through them. So I want to give an example. Let's take a look at A. Perhaps you look at A and you say, okay, it's a sine 270, and so I'm going to use rotation angles, and I know that 270 degrees is going to put me on my negative y-axis. And perhaps this was a situation that you found more difficult anytime our terminal arm finished on an axis. You then had to try to imagine your terminal arm really being here and therefore constructing an imaginary triangle. We may have struggled through that process. What I'd like to do is I'd like to take what we've learned this section, this unit, and see how we use it. That if I was ever asked to go through and deal with the sine of 270, I use my trig curve. And so what I end up thinking about is, well, I have a quick set of axes, and I know 270 puts me on an axis. So if I think about my trig curve, well, my sine curve starts in the middle and rises. That's all I really need. I don't even have to draw the rest of the curve. I can map it out in my mind and see what value of the function I come to for an angle value of 270. I'm going to continue the graph, but we'd never need to see it. You wouldn't need to draw it. That we could then say we know we hit our maximum at 90, we hit our 0 at 180, and we hit our minimum at 270. See, I already have my answer. I know then that when I get to 270, the value of that is -1. And by using our trig curves, that might help us to get there faster. So let's take a look at B. I recognize the angle value of 180, and that would put me on an axis. And so I'm going to think about my cos curve. Well, I know my cos curve starts at the top and falls. And now I can map my way through my cos graph to figure out the value of the function. So I know that I start at my max, I fall to 0, and then I have my value again. At 180 degrees, I know the value of cos is -1. And so those would be two instances where we would use our trig function to become a little faster and probably more confident in our answer. Take a look at question C, because I don't want everybody to think that, well, trig curves are the way that we should go all the time. If I was given a question like C, where I've been asked to come up with the value of tan 240, and I know that 240 doesn't put me on an axis, then I would still go back and use rotation angles, figure out my related acute angle, label the sides on that triangle, and therefore come up with your tan ratio, which is opposite over adjacent. Done. So take a look at A and B and notice those actually make life a little bit easier, the use of the trig curve. But if it's not on an axis, then I'm probably still going back to rotation angles like what we saw in C. Okay, let's work our way down to problem 4 now. What you'll see in problem 4 is a similar case to what you saw. We've already gone through and solved trig equations before. We used rotation angles to do so. I'd like us to notice, though, we have a couple instances where maybe we have a better method now. So take a look at A and B, and you'll notice that you have sine x or cos x equaling 0. And so that problem is asking you, for what angle of x does your sine give you a value of 0? Well, for me to go through and do that, I would every single time use my trig curve. So if I think about a quick set of axes, then I know that my sine curve starts in the middle and rises, well, then I could map that through in my head. That I know that since I start at the middle, one of my angle measurements that gives me a 0 is 0. I know I hit my maximum at 90. I know I come back at 180. I know I hit my minimum at 270, and I come back and hit my maximum at 360. My trig curve makes me so much faster to be able to solve that equation. What I'd like you to do is to pause the video now and give B a shot. Go ahead. Okay, we're back. So we see that we've got cos of x, we're solving for x, and our trig ratio this time is cos. So since I'm looking for a value of 0, I know that that's a key value on a sine or a cos graph, so I'm going to think about my cos curve. I know my cos curve starts at the top and falls. So when do I get to a value of 0? Well, I get there at 90 degrees. I then come through and hit my minimum, and I get there again at 180 degrees. Done. So if we happen to see any sort of trig equation where you have sine x or cos x equaling 0, 1, or -1, the key values on your trig graphs, then I would absolutely be using my trig curve to be able to answer that problem. If we take a look again at problem C, now root 3 over 2 is not a maximum, a minimum, or a 0. I'm going to still go back and deal with my rotation angles. My sine is negative, sine is opposite, so opposite is negative if I go down. Now I can create my triangles, opposite side, hypotenuse, opposite side, hypotenuse. I recognize then that that's going to give me 60-degree related acute angles, and therefore, to answer the problem, x would have to be in the third quadrant or in the fourth quadrant. So again, we notice that if I have a key value, my trig curves make me more efficient. If I notice that I'm falling somewhere in between, then I'll go back and I'll deal with my rotation angles. So hopefully that gives you a sense of how we can use our trig curves to get a little better as we work our way through. Okay, so what you'll notice on the next slide is that we're actually going to move into transformations of our trig curves. And we're going to take this a little slow, and we're going to use this as an introduction to what we're going to talk about next time. So what I'd like you to do really quickly is I'd like you to put down a sketch of your base function. So let's take a look at A. You've been asked to graph y equals 3 sine x. And so if we're going to graph y equals 3 sine x, then let's put down a quick sketch of what sine x looks like. So all we want to do now, put on your sine x. So we should be able to do that in like 15 seconds because you know your sine curve so well. You know your sine curve starts in the middle, hits its max at 90, 0, 180, minimum 270, 0, 360. And so you connect that with a smooth curve. And that would be our sine curve. Well, now what I'd like you to do is I'd like you to graph what 3 sine x looks like. And we should be good to be able to interpret what multiplying by 3 on the outside of a function would do to your graph. So if you're really confident with it, pause the video, go ahead and graph it. Okay, maybe we're back and we've already got a picture and we're looking for confirmation. Maybe we're not so confident because this is the first time we're really transforming a trig curve. My 3 on the outside is going to give me a vertical stretch by a factor of 3. And so all the values are going to be 3 times the distance to the x-axis. Well, if I'm on my x-axis, I had no change. This maximum at 1 would now get stretched up to a maximum of 3. Be very careful to make sure that you've been stretched to a value of 3 units, not 3 grid lines. Look at your scale. Your scale is 0.5 on your y-axis. Value of 0 wouldn't move. It would be invariant. -1 would get stretched down to -3, and my 360 would stay the same. And so my graph would then become this sort of graph. For y equals 3 sine x. So that should just give us a little confirmation as we work our way through dealing with the transformation. What I'd like you to do on B is to tackle both graphs at the same time. Let's put on a quick sketch of what our base cos curve looks like. And then let's go ahead and put on what the whole graph looks like, focusing on the effect of what multiplying by 1/2 on the outside of the function does. So let's pause the video now, give it a shot. Okay, we should be back. So when you take a look at B, we've got our cos graph. We know cos starts at the top and falls. Hits my 0 at 90, my minimum at 180, my 0, 270, maximum 360. Connect them with a smooth curve, and you should be getting pretty fast at this. So you might be able to see how we can get to our base graph in 10 to 15 seconds. Now I see that 1/2 on the outside, and I know that that's going to be a vertical stretch by a factor of 1/2. That means every y value is half the distance to the x-axis. So this maximum that was at 1 is now transformed to 1/2. 0 doesn't move. -1 gets stretched to -1/2. 0 doesn't move. And same thing for the final max. And so your graph then becomes this flatter curve. And so what we should end up getting then out of both of those situations is we've learned how to vertically stretch a trig curve. But more importantly, I'd like to make a note of something that's very important for us as we go. I'd like you to take a look back at both of those graphs, and I'd like you to determine the amplitude for both of your transformed graphs. So let's go back. Let's pull out some old terminology we should be good with. What is the amplitude of the graph in A? Well, you go all the way up here from a height of 3 down to a height of -3. So the total height of the curve is 6 units. I know amplitude is half of that, so my amplitude is 3. You take a look at your second graph. We go from a maximum of 1/2 to a minimum of -1/2. That makes the height 1 unit, and amplitude's half the height, so our amplitude becomes 1/2. We might be able to see something very important as we take a look at the equation of those graphs in a little more detail. I hope that we can see that you can always read your amplitude of your curve directly from the equation. Key feature for us. Key feature for us. And let's take that one moving forward. Okay, now that we have that one dealt with, then what we want to do is we'd like to deal with a different transformation. So when you take a look at the bottom of that page, now what I'd like you to do is let's go really fast through C. You have 15 seconds to put down a graph of what your cos curve looks like, just your basic cos graph. Go ahead. Okay, we should be super fast to be able to do that. And there we go. Okay, now we need to address what that 3 is going to do. That 3 is attached by multiply, so it's going to be a stretch. except we're stretching it on the inside of the function. That means we have a horizontal stretch. Also, I hope that we recognize that since we're doing it to the inside of the function, we've got the opposite effect. So if we're multiplying by 3 on the inside, that means our stretch factor is actually 1/3 of our graph. So what we'd like to do now, let's go ahead and take every point on that red curve and let's make it 1/3 the distance from the y-axis. So if I'm on the y-axis, then it doesn't move. This value 0 that used to occur at 90 degrees is now going to occur at 1/3 of that, 30 degrees. This value that was the minimum at 180 degrees would now occur at 1/3 of that, 60 degrees. This value of 0 at 270 would occur at 1/3 of that, which would be 90. And this value of 360, the max, would occur at 1/3 of 360, or 120. Now, some people will also focus in on the grid lines for that, and they can also examine that this value that was a 0 occurred on 3 grid lines, which means if I take a stretch of that of 1/3, it would only occur on 1 grid line. This minimum that used to take 1, 2, 3, 4, 5, 6 grid lines to occur, while 1/3 of 6 is 2, would now occur on 2 grid lines. You can use the grid lines. I would just be a little nervous as scales start to change. Instead, think about what the degrees would be. Now that you have all of those features, we can now connect them with our smooth curve. And there we go. Now, one important feature for that. What we have is one cycle of our graph. One cycle. But we were asked at the very top to graph that for 0 to 360. Notice we have only graphed that blue function from 0 to 120. It doesn't mean that we're going to continue to transform the points. We don't really need to think of it that way. Instead, what we can do is we can use that pattern to fill in the rest of the domain. Since we know that it is periodic, then that cycle is going to repeat over and over and over again. So let's repeat it. I know that 30 degrees from now, I'll get to my 0, and another 30 degrees I get to my minimum, and another 30 degrees I get to my, and another 30. That I can take that blue graph and I can stamp it out and start to fill in the rest of that domain. That's the nice part about dealing with periodic functions. If they repeat, then don't transform the whole thing. Get one cycle of it and use the repetitive nature of periodic functions to fill in the rest of the domain. There we go. Okay, let's do the same thing on D, but same thing as what we did before. Let's pause the video and let's get a base graph of sine x and then the transformed graph of sine 1/2 x. So go ahead and pause the video. We'll match up in the end. Okay, we should be back. I know my sine graph starts in the middle, hit my max at 90, 0, min, 360. Connect them. And again, 10 to 15 seconds and we've got our sine curve. Okay, now what does that 1/2 mean? We know that we're attached by multiply on the inside, so again, it's a horizontal stretch. But I need to remember that my factor is 2. So that means that all my points are going to be double the distance from the y-axis. So if I'm on the y-axis, I don't change. This maximum that used to occur at 90 will now occur at 180. This 0 that used to occur at 180 will now occur at 360. And I've noticed I'm off my grid. So the only portion of that curve that I can sketch is what I see on that blue. And so hopefully we match up and everything looks good between those graphs. Now, what I'd like to do in this scenario is I'd like to break down both of those graphs in a little more detail because there's two very important features that we can examine. So I'm just going to make these a little bit smaller so we have a little bit more room underneath the graphs. But a couple key features. The first one, and I use this one occasionally. I don't really lean on it that much, but it's important to note that if I was to ask you your number of cycles that exist in a first rotation, the number of cycles that exist in the first rotation. Well, you notice that our first rotation is 0 to 360. So when we look in graph C, how many cycles do you see on that graph? And you should notice, oops, I made that really small. You should notice that we get 3 cycles. If you take a look on graph D, how many cycles do you see on that? Well, we don't even see a full cycle. In fact, we only see from a 0 to a max back to a 0. That would be a half of a cycle. You might be able to look back into the equation then and notice that we can see the number of cycles directly from our equation. So that can help us at times. That when we take a look at a graph like C, y equals cos 3x, if we know that we're now going to have 3 cycles in that first rotation, then what we're going to end up seeing is a graph that's going to repeat much more often. In graph D, if we see that, well, we're only going to get a half of a rotation, then that should help us to confirm that our graph needs to be stretched out because we're only going to see half of a rotation. Okay, the second thing, and the thing that I lean on most, and the thing that you're going to hear me kind of refer to as like your best friend, especially when we get to problem solving, is that if we had to take a look at the period of each one of those graphs. So you should be good to be able to go through and find the period of each one of those graphs in C and D. Well, for me to find my period, maybe I go at the beginning, and that's where I get back. There was 1 cycle, and how long did it take to complete that cycle? 120 degrees. In graph D, I only see half of a cycle. So if half of that cycle takes 360, then if I was to continue that graph and finish it off, I know it would take double that, or 720 degrees, to complete its period. There's a really important key feature there. It's hard to see it in the equation, but it's a key feature for us that you want to have in your back pocket. As I said, I'm going to refer to it as your best friend. That your period is always 360 degrees, what your usual period is on your curve, divided by your k value. And we're going to grow to kind of know that we tend to refer to that value as your k value. So as a little quick confirmation, if I have a 3 attached to my x, then 360 divided by 3 gives me 120. And that should make sense a little bit, because if my normal period on my graph is 360, and a 3 on the inside of my graph causes a horizontal stretch by a factor of 1/3, then I need to take what used to occur over 360 and shrink it down. It's now going to repeat in 120. If I take a look at the graph in D, I see the same feature. If I took 360 and I divided it by 1/2, then that gives me 720. And it confirms my transformation. that if having a 1/2 in there means that I'm going to have a horizontal stretch by a factor of 2, then what used to occur in 360 degrees will now need double that. It repeats in 720. So what this last page was for us was just a little bit of practice at stretching our trig curves. A vertical stretch in A and B, a horizontal stretch in C and D, and that's going to help us as we move forward to tomorrow. It also gives us a little bit of properties in being able to recognize your amplitude from your equation and the number of cycles and your period when dealing with your K value. So what you really want to focus in on then is making sure that you have a good sound foundation of what we talked about today, and then we kind of gear up for transformations and graphing trig curves on our next day. Good luck.